Have you ever wondered how other electric charges will interact if they pass nearby an object with a known amount of net charge? That means if in a space huge amount of charge is present on a body, what will be its effect on other smaller bodies which are placed near to it? In order to understand this statement clearly or in detail, you must know the concept of the electric field. Now, in order to understand the concept, let us imagine a situation where we are having a charged body plus Q in the space called as the source charge, and another test charge having a small charge on it called as the test charge body, denoted by the Q naught. It is initially free to move in a space because it is not under the influence of this plus Q source charge. Now, whenever we place a source charge in a space, the region around it gets modified because of its present, and this modification we have shown by the electric field lines, that they are the imaginary field lines. Whenever the test charge will come under near this source charge, it will experience a kind of a force that is because of the presence of the electric field. Here lies the concept of the electric field. Now, so let us understand the another situation where we are having the same source charge which is present in the space. Here we have the same source charge, but this time a test charge is placed near to the source charge. So now it will experience a kind of a force. Now, from where does this force come? This is because of the presence of the electric field around the source charge. This electric field will exert a kind of a force on the test charge, and this is all about the concept of electric field. That means it helps us to find out the magnitude of the force experienced by the other smaller bodies. Now, next we have the concept of the electric field. Now, let us begin with our important topic, that is its definition and what are the important steps in its derivation. So, what we are having first, definition. How we can define it? It is defined as the electrostatic force per unit test charge acting on a vanishingly small positive test charge. As I have shown you, if we are having a source charge plus Q placed in a space, the region around it gets modified by the presence of the electric field. Now, if a test charge is placed near to the source charge, it will experience a kind of a force. Now, mind it here, the test charge have to be the vanishingly small. Why is it so? That is how we can represent it. We can represent it as a limiting case of Q naught is tending to 0. This is the very important part in defining the electric field. So, what will be the definition? It is defined as the limiting case where Q naught is tending to 0 force per unit test charge. Now, I will explain why we should need a vanishingly small positive test charge. But before that, let's go for the electric field. Here, E is a vector quantity. Why? Because its direction is same as that of the force F experienced on a positive test charge. If we are having a test charge is placed, just a minute, let me erase. So now, if we are having a test charge placed in this at this point, so it will experience a force in this direction. If we place the test charge at this point, it will experience a force in this direction. Or if we place a test charge in this direction, it will experience a force. So, whatever, depending on the position of the point charge, the direction of force keeps on changing, and hence the direction of electric field keeps on changing. That is why we call it as a vector quantity. That means its direction is same as that of the force experienced by the test charge. Now, there is one concept check. What it has to say for us? That means the test charge Q naught, it may disturb the charge distribution of the source charge, and hence it may change the electric field which we want to measure. If we take this Q naught to be of measurable quantity, that means if it is of a certain big amount of quantity, 1 coulomb, 2 coulomb or certain microcoulombs, that means its presence can affect the presence of the field lines of the source charge, which we do not want. That is why in the definition we have defined Q naught is tending to 0. We cannot take the value of Q naught exactly 0, but it is tending to 0, 0.000 something coulombs. Value should be 0.00 in millicoulombs. That means the test charge Q naught must be small enough. Why? So that it does not change the value of E. So, in definition, if you give this point, it will be wrong statement. In definition, you have to give only this much statement in limiting case. Next, we are having units and dimensions of electric field. What are the units? First of all, as it is, electric field is defined as the force experienced per unit test charge. That means the unit of force is Newton, and for charge we have coulomb, so Newton per coulomb, or it is also called as volt per meter. Now, for the dimensions of electric field, as electric field is the force per, that is electric field is force per charge. That means mLT minus 2. It is the dimensional formula of force, and coulomb is the dimensional formula of test charge. So, on solving this, we will get mLT minus 3A minus 1 will be its dimensional formula. Next, let us try to understand the physical significance of the electric field. As I have shown, the electric field lines are shown by this cases if we are having a plus Q source charge. That means the force experienced by the test charge Q naught is different at different points. So E also varies from point to point. As I have explained, if Q naught, the position of Q naught keeps on changing, so the direction or the value magnitude of electric field also keeps on changing. That is the important factor. So what we can say that E is not a single vector but a set of infinite vectors. So many vector directions are associated with the electric field. So we can say it is a set of infinite vector, not a particular direction. In a particular situation, it is having particular direction, but in a lump sum quantity, we will say we can have all the possible directions. So electric field is an example of a vector field. Next, by knowing the electric field at a point, we can determine the force on a charge placed at that point. So in spite of not using the Coulomb's law, we can also find the force in terms of the electric field. So this is its physical significance. It helps us to find the force experienced by a charge placed near a source charge. Now there is one key point. What is that? The electric field is the characteristic of a system of charges. That means this electric field is the characteristic of the source charge, not of the test charge. So mind it here carefully. Electric field is the characteristic property associated with the source charge or a system of charges. It is independent of the test charge. It will there in a test charge has no significance in its formulation. That is the important key point. Next, we will go for the derivation, the steps that you will be writing in exams or whenever it is any question related to this concept is asked. If you will follow these steps, you are going to get the full marks. Let's see what are the steps. We are first finding the electric field due to a point charge. For that, let us imagine a situation where we have placed a point charge called as the source charge at the point O. Now at a point P, we want to find its effect, that is what will be the electric field intensity at the point P. So we have to place a test charge of vanishingly small magnitude at the point P. Now naturally this Q naught will experience a force in this direction. Why? Because they are of the similar nature. So it will experience a force in this direction. Now the separation between the Q and Q naught is R. Now, what will be the Coulomb's force experienced between this Q and Q naught? Already earlier we know already that it is 1 upon 4 pi epsilon naught Q naught by R square, and this is the unit vector R which is pointing from O to P. Now, according to the definition of the electric field, what is that? Electric field is E equals to F upon Q naught. So, if you divide this equation by Q naught, so this Q naught and Q naught gets cancelled out. That is why in my previous article I have told you that electric field is independent of Q naught. It has nothing to do with Q naught. It is the characteristic property of Q only. So what magnitude wise or in formula we will get for the derivation is 1 upon 4 pi epsilon naught Q by R square and unit vector R, that is it is pointing in this direction. That is, it is just a characteristic of the source charge. It has nothing to do with the test charge. So what will be the final magnitude wise if you want to write? It is simply equals to K Q by R square. That means it varies inversely with the R square. Next, we will try to understand the certain key points. What are the key points? As we have seen that the electric field varies inversely as R square. That means at all points on the spherical surface drawn around the point charge, the magnitude of E is same. That means if we will have a spherical surface, if we will draw a spherical surface like this around a source charge, at all the points on this spherical surface, the magnitude of E is going to be the same. That is called as and it is independent of direction of R, and this is called as the spherically symmetric or a radial field. That is the most important point. Why the electric field is a radial field or a spherically symmetric? Because at all the points on the spherical surface drawn around the point charge, the magnitude of E is same. That is why it is called as the spherically symmetric. Now, what is the importance of the electric field? Now, by this time you might have understood that electric field is a measurable effect generated by any charged object. It is called as the measurable effect generated. Next, in order to understand the nature of action at a distance force, so nature of action of the force, whether the force will be repulsive or attractive, the concept of electric field helps us to determine that. Now, next we are having the electric field lines, how we can represent the electric field lines. In case of a positive source charge, the electric field lines always point away from it. Always keep this in mind, they will always point away from it, because the test charge that we have taken Q naught, it is positive in nature. So naturally a repulsive force will be acting on the test charge, so electric field lines will be pointing away from the source charge. But if we are having a source charge as negative and we are having a positive test charge, mind it, here we have taken a test charge as a positive, so there will be an attractive force acting on this test charge. So electric field lines will always be pointing towards the negative source charge. Keep this in mind. For a negative source charge, the electric field lines are towards it. Now we are having one knowledge test. Let's see what the knowledge tests have. So here are some questions that are related to this topic that can be asked in board exams. If you have understood it well and write all the steps that I have explained, you will get the full marks. So go for these questions and present your answer very well. All the necessary steps which are required to explain the answers of these questions I have already explained. Now let's go for some numericals. Before we go for the numericals, we have a quick recap what I have taught in my previous videos. I have taught you about the concept tips on Coulomb's law. I have already dealt with the concept tips on superposition principle and numerical tips on Coulomb's law and superposition principle, which is very, very important. Please go for them also. You can get lots of knowledge from it. Now let's start with some numericals. Here we go with our first numerical. Let's see, the 2-point charges +1 microcoulomb and +4 microcoulomb are kept 30 centimeter apart. How far from +1 microcoulomb charge on the line joining the two charges will the net electric field be 0? How to depict the given situation in the form of a figure? Let's see, we have placed the one charge Q1 which is +1 microcoulomb at the point A, the other charge Q2 at the point B. These A and B are separated at a distance of 30 centimeter. Now let us suppose P be the point where the net electric field is 0. Now at the point P, we want to compute the directions of electric field E1 and E2 which were due to Q1 and Q2 respectively. Let us see first E1, it is due to the Q1. Now Q1 is positively charged, so at the point P, the electric field due to the Q1 will always be pointing away from the positive charge. That is, its direction will be this one. Similarly, if we go for the direction of E2, E2 is due to the +4 Q microcoulomb. +4 microcoulomb, so it is due to again positive charge. So at the point P, the direction of E2 will be pointing away from the charge Q2. That is, E1 and E2 they are pointing in opposite direction at the point P. So diagrammatically we have shown them in the sense of direction. We have shown them E1 and E2. Now we can find the magnitude of E1 and E2. Further, let us suppose the point P is at a distance of x from the point A, and the remaining distance, that is the distance between P and Q2, will become 0.30 minus x, where we have converted it into meters. Now next, what we can have, the electric field at the point P will be 0 when we have E1 equals to E2 as they are pointing in opposite direction. Now the formula for E, already we know that it is KQ by R square. So if we will put this formula for our particular situation, what we will get? E1. Let us see E1 K, that is 1 upon 4 pi epsilon naught. E1 is due to the +1 microcoulomb. So here we have converted into coulomb as 10 to the power -6 coulomb upon R square, that is the separation between A and P is x. So we have taken x square. Similarly, if we want to find the value of E2, same magnitude. So 1 upon 4 pi epsilon naught. Here E2 is due to the +4 microcoulomb. So we have converted it as 4 into 10 to the power -6 coulomb upon the separation between P and Q2. It is 0.30 minus x whole square. Now on cancelling the certain like terms, we will get the next step. The next step will be this step, and on solving this, we will get this value. If we will solve this equation, what we will get? X equals to 0.10 meter, that is 10 centimeter to the right of +1 microcoulomb charge. That means from the point A, if we have the 10 centimeter of distance, there the net electric field will become equals to the 0. This is how you can solve the numericals based on electric field. Now next, go for the next numerical. The 2-point charges +16 microcoulomb and -9 microcoulomb are placed 8 centimeter apart in air. Determine the position at which resultant electric field is 0. That means how to depict it? If we place +16 microcoulomb at the point A, this is Q1. Q2, which is -9 microcoulomb at the point B. The A and B, they are separated at a distance of 8 centimeter in air, and P is the point where the net electric field we want to compute to be the 0. Now our first target should be to find the direction of E1 and E2. Now since E1 is due to Q1 charge which is positive, so always in this direction it will be pointing away from the positive charge. So at the point P, this is the direction of E1. Now E2 is the electric field due to the Q2 which is negative charge, so its direction will be always towards the negative charge. So that is why at the point P, the direction of E2 is towards Q2. Direction of E1 is away from Q1. Keep this in mind. And now these E1 and E2, they are pointing in the same direction. Now further, let us assume that the point P is at a distance of x centimeter from the point A. So the remaining distance between P and Q2 will become 8 minus of x. Now we want to find it magnitude wise. What we can have, if P is the point where the net field is 0, so what we can have at the point P, we have E1 plus E2 equals to the 0. Why? Because E1 and E2, they are pointing in the same direction, so when they will add up, then only they will give us the net electric field as 0. Now again, the magnitude of E is equals to KQ by R square. So on putting the magnitudes, K is there. Now this E1 is due to Q1, which is plus 16 microcoulomb. So here we have converted into coulomb as 10 to the power minus 6 upon separation is x minus 10 to the power minus 2. Why we have included? Because we have converted centimeter into meter. Similarly, E2 is due to minus 9 microcoulomb. So here we have converted it as minus 9 into 10 to the power 6 coulomb, and the separation is 8 minus x, and we have converted into meters, and this is whole square equals to 0. On solving this and cancelling the like terms, we will get this step. Further, if we will cancel the steps, we will get this equation, and now the value of x comes out to be the 32 by 7 or 32 centimeter. Two values we will get for x because we are having plus minus sign. Now, if we see the situation, x equals to 32.7, that means x comes out to be the somewhere between 4 point something value. That means it lies between A to B. Now, in between A to B, what we are finding, if we have a point P where electric field is to be the 0, it can never be 0. Why? Because E1 and E2 in between A and B will always be pointing in the same direction. So, this particular situation we have to neglect, where the net electric field can never become 0 in between A and B. Now, next, how can we find the other point? Now, let us, the remaining point is x equals to 32 centimeter from A. That means if we move from A towards 32 centimeter, that is towards the right of Q2. That means in this somewhere over here, towards the right of Q2, there E1 and E2 will be pointing with there. See here, E1 will be pointing in this direction towards the right, and E2 will be pointing opposite to E1. So this is the point P where E1 and E2 can cancel each other, and the net electric field will be the 0. So mind it, when we are having the two unlike charges, that is one is positive and negative, so the net electric field will be 0 always on the other side of the charge. That is, it will never be in between the two charges. So at x equals to 32 centimeter, the electric field will always be the 0. This key point you have to keep always in mind. In between A and B, the net electric field can never be 0. Next, go for the next question. Now we have 2 point charges plus 6q and minus 8q are placed at the vertices B and C of an equilateral triangle ABC of side A. Obtain the expression for the magnitude resultant electric field at the vertex A due to these two charges. So this is the given figure. ABC is an equilateral triangle where at the point B we have placed a plus 6q charge, and at the point C we have placed minus 8q charge. Now our aim, this equilateral triangle is of side each of side A. Now our aim is to find the net electric field at the vertex A. So how we can find it out? Now at the vertex A, this plus q charge will be exerting a force or the electric field in this direction because it is positive. So this is EBA. It is denoted by EBA, electric field pointing from B to A, which will be pointing away from the plus q charge. Now next we want to find the electric field due to this negative charge which is at the C. So negative charge at the point A will take the electric field towards itself. So electric field at the point A will be pointing towards the negative charge. So this is the direction EAC, that is electric field pointing from A to C, it will be in this direction. Now diagrammatically or direction wise we have represented the electric field B and electric field C. Now what will be the resultant electric field at the point B? It will be the vector addition of EBA and EAC. Now let us see what will be the vector addition. How we can compute? Here the magnitudes of EBA. Now the general formula for electric field is KQ by R square again. So here this EBA, it is due to the plus Q charge. So here we have to put Q as 6Q, and the separation between the A and B is A. So that is A square, that comes out to be the 6E. Now here for simplicity we have substituted E as a general formula 1 upon 4 pi epsilon Q by A square. So this Q by A square complete part we have substituted as E. So our EBA becomes 6 of E. Next we want to find EAC. Now what is EAC? EAC is due to the minus 8q charge. So here we have to put the magnitude of 8q upon A square, that comes out to be the 8E, where E is equals to 1 upon 4 pi epsilon Q by A square. So 8 into E we will get EAC. Here we are not putting the magnitude that is negative charge, here only we are keeping the magnitude part. Now let us see what will be the net electric field. The net electric field at this point will be always equals to the, Here the net electric field is the vectorially we have to add. So what will be the vector addition of EBA and EAC? It will be the under root of EBA square plus EAC square plus twice of EAB EAC cos 120 degree. Now let us put the value 6E, 8E and cos 120 degree is minus 1 by 2. On solving this value, we will get the formula for E net as equals to the E net equals to the E root 52. And now we will put the value of E as 1 upon 4 pi epsilon naught Q by A square. So this complete part becomes the magnitude of net electric field at the vertex A of an equilateral triangle. So here certain key points that you have to keep in mind is that vectorially you have to add these two electric fields because this is a vector quantity and the angle between them matters a lot. So we have to put the value. Next, go for the other question. 4 charges plus Q, minus Q and minus Q are placed respectively at the 4 corners A, B, C and D of a square of side A. This time it is a question based on a square. Calculate the electric field at the center of the square. Now let us see how we can depict the given situation. Here A, B, C, D are placed at the corners of a square. Now plus Q and plus Q are placed at A and B respectively. Similarly, minus Q and minus Q are placed at D and C respectively. I think this will be clear to you. Now, at O is the center of this square where we want to compute the net electric field. Now, let us see step by step. First of all, we will take the plus Q charge at the point A will exert an electric field in this direction. Why? Because it is a positive charge. The electric field will be pointing away from the plus Q charge. So, this is the direction of EA. Keep this in mind. Similarly, the charge plus Q which is placed at B will exert an electric field EB. Again, it will be away from the, it will be pointing away from the plus Q. So, at the point O, we have to draw this. This is the direction of EB. Next, C. The direction due to EC, that is direction due to C minus Q charge. Now, at C, minus Q charge is placed. So, the electric field due to a negative charge always points towards the negative charge. So, this is the direction of EC. From O, EC will be pointing towards the negative charge. Keep this in mind. Similarly, at the point D, we have placed a negative charge. Again, ED, the electric field which is due to negative charge will be pointing towards the point D, that is towards the negative charge. So, this is the direction of ED. I hope now the direction will become clear to all of you. Once again, I will show it to you. EA is in this direction away from plus Q because it is due to positive charge. Similarly, EB is pointing away from the plus Q because again it is due to positive charge. EC is towards the negative charge. It is in this direction. Similarly, ED is also towards the negative charge. So, these 4 directions you have to keep in mind. Rest magnitude wise, we can find the value of the electric field since all the charges are of equal magnitude. Here, the charges are of equal magnitude Q, Q, Q and they are at the same distance R from the center. Now, see here, the distance of O with respect to A, with respect to B or with respect to C or with respect to D, it is equal, which is equals to R. So, this R distance we have to compute. Now, here it is already given that the side of a square is A and here the side of the square is A. So, how we can find the value of this R? This R we can compute it in the form of using the right angle triangle. Here if we are having a right angle triangle like this much, if they are at right angle, this is R and this is A. So, what we can have, the magnitude of EA, EB and EC each will be equal and that is equals to KQ by R square. Now, the value of R using hypotenuse theorem, we can get it as A by root 2. So, now we will put the magnitude as KQ upon A by root 2 whole square. So, that becomes 2 into KQ by A square. This is the magnitude of every magnetic field, that is EA, EB, EC and ED. The direction I have mentioned in the figure. Now, let us see E1. Now, we want to find the value of E1. Let me clear the figure first. Now, E1. Now, first we will find E1, which is the EA plus EC that is pointing in the same direction. So, EA and EC, they are pointing in the same direction. So, we will be having E1 is the net electric field. So, magnitude wise, we have to simply add up these values. That is, EA is 2 into KQ by A square. Similarly, 2 into KQ by A square. So, on adding, we will get 4 KQ by A square. Now, next, what we will be having? E2. What is E2? E2 is pointing in this direction. EB and ED, they are pointing. So, we have to add these two electric fields. That is why we will get E2, which is EB plus ED. Again, on the following the same line on the previous step, we will get E2 as 4 KQ by A square. So, what is E1? E1 is the net of EA and EC. Similarly, E2 is the net of EB and ED. Next, we want the net electric field. So the net electric field will be equals to the under root of E1 square plus E2 square. So now the sum of this and this will give you the net electric field. So magnitude wise we have to add up this value and this value. Ultimately it comes out to be, on solving this square or square root, we will get 4 into root 2 k cube by a square. So this